Organic reactions overview. And here's a bunch of complex organic reactions that we won't be getting into quite that much detail. So we're going to look at three general types, and we can break them up into what's really happening in the reaction. Addition is one of them. We're adding things together. Substitution, where we're switching things out. And then elimination, where we see a couple of other interesting things like oxidations happening. We're going to cover what goes in and comes out of these reactions, so the reactants and the products. We're not going to get into the conditions necessary to get the reaction to happen. That would be an additional step that we're not going to be doing. So first, addition reactions, essentially things being added together. Think of it like a synthesis reaction, but with organic chemistry. Alkenes can be used for addition reactions. They have this double bond on them, and so we can think of that as a potential to break that double bond and then add addition reactions, add things to them. So a little bit more options in terms of their reactivity than an alkane may have. So first type, and again, major subcategory of an organic reaction would be an addition, but then we can think of the actual subcategories like halogenation, where we can take any alkene that has that double bond on it, and we can add to it a halogen, and so we're just straight up a halogen. And so we've got something like chlorine, and by doing so, we'll end up with an alkyl halide. So as an example, you can imagine an alkene. So let's say we've got this butene here, and this is one butene. We've got 1, 2, 3, 4 carbons, so butane without the double bond coming after the first one, so this would be our 1-butene, or maybe but-1-ene. So that as a example reaction. If we add to it a halogen, so let's say our chlorine, then what's going to happen is essentially where this double bond is here, the first carbon and the second carbon have two shared pairs of electrons. If we were to remove that double bond, it essentially opens up a spot to put one of the chlorines on one carbon and the other chlorine on the other carbon. So we'd end up with our 1,2-dichlorobutane now, because we've lost the double bond out of it, and that's the alkyl halide being produced. So an addition of a halogen onto a alkene with the double bond by breaking the double bond and then putting the two chlorines on there. So we'd end up with our 1,2-dichlorobutane. Next, we can do the same thing with hydrogenation. So instead of using any of the halogens, we can use, that's a 2, H2. And essentially why this one's kind of gets its own category is because you can imagine, let's do, I don't know, this one here, which again is butene, but the double bond is coming after the second one, so we'd say this is not 1-butene. I hope I named the last one 1-butene, but this is 2-butene, and because of the double bond not being on the end carbon, this is actually also a potential for either a cis or a trans isomer. There are two types of 2-butene, cis 2-butene or trans 2-butene. This particular one, we have a bond going on this side, we have a bond going on that side, so they are transverse of each other on either side of the double bond, so we'd call this trans 2-butene. Anyways, we add our H2 to this, and we would end up with our alkane, because we're essentially saturating our hydrocarbon. And we'd have our 1, 2, 3, 4 carbons there. And again, think of it as we used to have a double bond there. We have now removed that. And so that means that carbon number 2 here and carbon number 3 here now have the ability to pick up another hydrogen. Now, because it's a hydrogen bonding to it, and because these are line diagrams, we don't draw the hydrogens being bonded to it. So essentially, we would just get rid of the double bond, place a hydrogen, though we don't see it, on carbon number 2, and a hydrogen on carbon number 3 as well. So our hydrogenation essentially saturates our alkene, which used to be unsaturated. So we're hydrogenating these. You could do it with something like vegetable oil that starts off being vegetable oil unsaturated. You hydrogenate it by adding hydrogen to it, and you end up with a saturated, or at least it's more saturated vegetable oil that you had before, and making it something like margarine. All right, combine the two, hydrohalogenation. So if you take any hydrogen halide, so let's say, I don't know, HCl like that. Again, we're using alkene, so let's switch it up and let's use a, I don't know, 1-pentene. And if we add to this a molecule that has 1 hydrogen and 1 chlorine, again, it's an addition reaction. So we take our 1-pentene or pent-1-ene, and we're going to be putting the hydrogen on one of the carbons. So we've got carbon number 1 and we've got carbon number 2 there. And let me just draw the original with the double bond there. So again, imagine the double bond opening up. Carbon number 1 is able to take one of these guys, and carbon number 2 is able to take the other one. Now, because they are not the same thing, it's not 2 hydrogens or 2 chlorines, it is a hydrogen and a chlorine, their placement is going to be dictated by Markovnikov's rule. And what that says is like the rich get richer, or the carbon that has more hydrogen gets more hydrogen. So whichever of these 2 carbons has more hydrogen, that's where the hydrogen ends up, and then the chlorine ends up on the other one. So if we think of originally, let's draw the original. We've got our alkene here. So if we were to show the hydrogens, which in a line diagram we don't, but this one on the end has room for 2 hydrogens. This guy here, because it has 3 bonds already, only has room for 1 more hydrogen. So carbon number 1 has more hydrogen, so it will get the hydrogen. So I'm going to get rid of those guys. So when this double bond breaks, carbon number 1 gets the hydrogen, carbon number 2 will get the chlorine, according to Markovnikov's rule, and we will end up with 2-chloropentane as the product of this hydrohalogenation. Hydration, same idea. Think of water as being a hydrogen and a hydroxide attached together as a molecule. So if we have a double bond, we can do the same thing. We sort of split it up, and so imagine the hydrogen is going to end up in one place. We know where that's going to go according to Markovnikov's rule. The hydroxide ends up on the other, and because we now have what used to be an alkene, which now is an alkane, with an OH group on it, it's going to be an alcohol. So let's say we had our, let's do better drawing than that, our double bond on a 2-carbon chain. So this is prop 1-ene would be a name for it. Now there is no other type of propene, so you can just say propene. And we're going to add to that our water, hence the name a hydration addition reaction. And so when this propene's double bond is broken, we've got carbon number 1, we've got carbon number 2, and one of them gets the hydrogen, the other one gets the OH, the alcohol group. And Markovnikov's rule will say the one, let me draw the original again, this carbon number 1 has 2 hydrogens, this carbon number 2 has 1 hydrogen based on the bonding of the other carbons. And so the carbon number 1 is going to get the hydrogen, and the alcohol then is going to go, once we break the double bond, the OH group, which is not an ion, so it's not hydroxide, it is going to be covalently bonded, so it's an alcohol group, and that is going to go to carbon number 2 according to Markovnikov's rule. And we'd end up with our 2-propanol or propan-2-ol as our product of this hydration reaction, isopropyl alcohol, rubbing alcohol. Aldehydes and ketones can also do addition reactions, and so we can talk our aldehyde do a hydrogenation, so adding hydrogen to it as well. So let's pick a simple aldehyde, and remember our aldehydes have their double bonded O's. Let's go with, I don't know, that's not enough room. Let's make it pentene so I can point it down. Get rid of that guy. So let's say we had a 5-carbon chain with an aldehyde group on the carbon number 1. So this would be 1-pent and al, because it's an aldehyde group. And again, it lowest number, so that becomes carbon number 1. What we can do is we can hydrogenate this one as well. And essentially, it's the same idea as that. Let's draw the original, and then we'll break the bond. So we originally have this double bond, This time it's between a carbon and an oxygen, but it's still a double bond. It'll open up like the carbon-carbon double bond. So if I break that double bond there, now this carbon here is looking to bond with someone, and now the oxygen looking for two bonds as well. We've got two hydrogens taking place here, so the hydrogen will get bonded on there, but because this is a line diagram, again, we don't draw the hydrogens, but we would write the one that gets bonded onto the oxygen. So this would be another alcohol, and because it is a alcohol group on a terminal carbon, it's a primary alcohol, and so we now have pent, that's not it, pent, and all, and because it is on carbon number 1, we should say 1-pentanol, because there is such thing as 2-pentanol and 3-pentanol, so we do want to name this one as 1-pentanol. Next, same idea. Let's do this with pentanone. And so this is a ketone because the double bonded O is not on a terminal carbon. It's on one of the middle ones. So you could have this one here is pentanone, and it is on carbon number, we count from this side, 1, 2, 3, or 1, 2, 3. So this is 3-pentanone, and 2-pentanone exists, so we want to make sure we label it. This can also be hydrogenated, and so we would end up with, let me draw the original first, and we'll break the bond. So we have that double bond there. It'll break. The middle carbon gets one of the hydrogens, but we don't show it in the line diagram, and the other one ends up attached to that oxygen, and so we'd end up with, in this case here, a secondary alcohol, because the alcohol group is not on a terminal carbon, it's on one of the middle ones, and this particular one happens to be 3-pentanol. Ran out of room. All right, alkynes having a triple bond, think same thing, but because you have two of those pi bonds there, you can break both ones of them. So think of it doing this addition reaction twice. And again, you can do it with the halogen, you can do it with the hydrogen, you can do it with the water. All of them would be addition reactions. So let's just draw, I don't know, let's go with our butane here, and this would be 1-butane. So what we could do is we could, let's, I don't know, hydrogenate it. Because there are two pi bonds here, that triple bond has 1 sigma and 2 pi bonds, what we can do is we can draw the original, we can break one of them and attach the hydrogens. Now it's a line diagram, we don't see them, but we can also do this twice. So we can either write it out twice, or we can do it with stoichiometry and say, okay, let's add 2 hydrogen gas molecules, a total of 4 hydrogens on there, and they would then break the pi bond, or this, what was a triple bond, and then became a double bond, and we just end up with our butane, or our saturated alkane here. Oh, there's an example of a halogenation showing up underneath there, and so this is our ethine, and we could add 2 bromines to it, and we'd end up with 1,1,2,2 tetrabromal ethane. Cyclical hydrocarbons, they, as long as we're not talking benzene here, but we're talking about a cyclical hydrocarbon that has a double bond on it. So imagine we had this cyclohexane with a double bond on it, making it into cyclohexene. Same thing can happen with it. You break the double bond. Those 2 carbons now have room to pick up. In this case, it's a halogenation addition reaction. So each of the carbons picks up 1 bromine, and you end up with 1,2-dibromal cyclohexane. All right, moving on to substitution reactions, where we are switching one thing out for another. So you can kind of think of this as kind of like a double displacement reaction, but the organic chemistry version one of it, where you break something apart and you switch the pieces up, and you end up from 2 reactants, you get 2 different products. So if we have an alkane, we can add a halogen to it, and we'd end up with an alkyl halide, and we'd be knocking off or switching off one of the halogen atoms for one of the hydrogen atoms that used to be on the alkane. So imagine, let's go with pentane, and if we add a halogen to it, so let's go with, I don't know, chlorine again, what would happen is this chlorine, which is again 2 chlorines bonded together, we would be switching out one of the hydrogens on the alkane for one of the chlorines. So let's imagine that we would have this original pentane, but I don't know, let's pick the carbon number 2 here. It originally has 2 hydrogens that we don't see in the line diagram. We could take one of those hydrogens and it would go off and leave with one of the halogens. But in doing so, because the hydrogen's not there anymore, it would leave behind the other halogen. So we're essentially switching out one of the halogens for one of these hydrogens that we don't see in our line diagrams, and we'd end up with a hydrogen halide and now this alkyl halide. And so in this case, it would be 2-chloropentane as our product here. We could keep doing this, so you could keep adding more and more of these chlorines and switching off more and more of the hydrogens until you get it sort of saturated with these halogens, and then you end up with things like our chlorofluorocarbons, which give you all sorts of options in terms of molecules. With the aromatic, so benzene is going to be able to do a substitution reaction. We did not see it doing an addition reaction. You can do that with a cyclical alkene, but in terms of benzene, remember benzene is, it looks like cyclohexane. However, it has this alternating double bond structure, which gives it this really stable arrangement that does not want to be easily broken. And so we kind of hint at that with our the cool way of drawing benzene, where we're saying, okay, those double bonds are alternating between the 6 carbons. It's more like you got 6 1.5 bonds than you have 3 double bonds, because they're going to resonate between back and forth. So we could just draw it like that, because again, with benzene, they are actually resonating between where I drew them in the one versus where I draw them in here. So they sort of resonate between those two. And so we draw benzene like that sometimes. That is a nice stable structure. But do remember, each of these carbons, again, it's a line diagram, so I shouldn't really be drawing this, but each of those carbons has a little hydrogen on it, because if you look at let's get rid of those false hydrogens. Oop, that's not what I wanted. There we go. If you look at each of these carbons here, they have 3 bonds, so we know that to be stable, they'd have that hydrogen on there as well. So benzene does have 6 hydrogens. So what we can do is we can substitute out one of those hydrogens, or more, with a halogen. So we do a halogenation with this. So let's start off with our benzene and let's halogenate it. Again, we don't want to mess with the double bonding resonance structure within there, but what we could do is add in, let's go with iodine this time. So we could imagine under the right conditions, we could add iodine to this benzene molecule, and what we'd end up with is still the benzene structure, but one of the hydrogens would get replaced with one of the iodines, and then the other iodine would leave with the hydrogen that it took from benzene. So we'd end up with this iodobenzene being produced. Here it is with bromine showing up underneath there, and again, substituting out one of the halogens for one of the hydrogens. Alkylation is where you can do something similar to that, but what you're doing is you're sort of sticking on a alkane and leaving with the hydrogen, with the halogen. So let's say we've got our benzene, and now if we just added, like, let's say 2 chlorines, we know that when the reaction took place, we would have one of the hydrogens from the benzene leaving with the other chlorine. But that wouldn't be alkylation, that'd just be halogenation. What we could do is we could say, okay, instead of just having 2 chlorines, what if we took something like, let's go with a propane that had a chlorine on it. Then the same thing can happen, is that this chlorine here can leave with one of the hydrogens, but in that case, it would, instead of just replacing the hydrogen with a other chlorine, it would actually replace it with this alkyl group. So you'd have the that's an ugly benzene. 1, 2, 3. All right. So there's our benzene, and so one of the benzene's hydrogens leaves with the chlorine, but in this case, it's a alkyl halide that we're using. In this example here, we would have chloropropane, 1 chloropropane. And so if we, let's say this was the carbon that lost its hydrogen, then it would end up with this propane, the 3 carbons there would end up attached to it, and you'd end up with this propylbenzene being produced. So that would be alkylating the benzene. There's another example with a methyl being dropped off, showing up underneath, and a methylbenzene being produced. All right, here's an example with an ethylbenzene, and again, the chlorine takes the hydrogen that's attached there that does not get drawn. The remainder for this structural diagram gets stuck on there, and we end up with an alkylation. If we do this more than once, we can stick together a bunch of things. And so let's go back to just the halogenation of benzene. So you stick one on there, and you'd end up with your hydrogen leaving with the other bromine, and you'd end up with bromobenzene. But if you did it again, and again, you could write a 2 there instead of writing it out twice, but if you did it again, so we took this bromobenzene and we halogenated it again, we would stick on another bromine. But it doesn't necessarily have to end up on, like, the first bromine, we'll call that being on carbon number 1. The second one could end up on carbon number 2, or on 3, or on 4. Now, it wouldn't end up on number 5, because that would turn number 5 into carbon number 3, rotating the molecule, lowest numbers. So you'd end up with 3 possible options here. So you could have 1,2-dibromobenzene, 1,3-dibromobenzene, or 1,4-dibromobenzene. 1,5-dibromobenzene is the wrong name for 1,3-dibromobenzene. Amines, we can see this again, and we'll start off with ammonia. So start off with just the nitrogen with 3 hydrogens on there. We can add, kind of like what we saw happening with the addition of an alkyl group to benzene, but in this case we can add it to a nitrogen. So if you start off with ammonia, and so imagine our NH3, and I'll actually write the 3's here, and an alkyl halide, so you can imagine, I don't know, let's pick a nice easy one. So let's go with chloromethane, so 1 single carbon attached to a chlorine. And if we did this, what's going to happen is, again, the hydrogen halides is produced. So the hydrogen that was originally on the ammonia is going to leave with the whatever halide you're using, in this case chlorine. And then that carbon that was on there is now going to be attached to, and I'll write the hydrogens on there as well, but now this nitrogen is going to have a chlorine attached to it. So, sorry, a carbon attached to it. So this carbon here essentially gets stuck onto the nitrogen here, and the hydrogen that used to be on the nitrogen leaves with the chlorine. So we'd end up with a primary amine. This is kind of an ugly looking primary amine. Let's redraw that. So a primary amine, 1 carbon in this case, because we had 1 carbon as our alkyl group on the halide. And if you want, you can write in the other 2 on there. It's kind of awkward in terms of positioning, but that nitrogen would still have 2 hydrogens attached to it. It's a primary amine. It only has 1 alkyl group sticking off of it. So our ammonia plus our chloromethane is going to produce this primary amine, and so we have a methylamine for this one, and just it's only got the 1 carbon on there, and the hydrogen halide being produced. Then let's say we took this primary, so let's run the other reaction. So let's take this product that we produced here, and so I'm going to take my primary amine. Let's stick with the same shape there. So just a line diagram for my primary amine would look like that. If you want, you could put the hydrogens on there. So let's do that. So this, we don't normally see them in line diagrams, but because it's a amine, let's write them. And let's add in another alkyl halide. So let's go with 2 carbons attached to, for fun, let's do bromine. So this 2 carbon, it's an alkyl, has 2 carbons, and it's a halide, so 2 carbons on there. So bromoethane in this case here. When they react, again, the bromine is going to leave with, we've got 2 hydrogens here, so the bromine is going to leave with, let's put the hydrogen first, the hydrogen, just like before, so we're producing this hydrogen halide. And what's going to happen is now this nitrogen that used to have 2 hydrogens is only going to have 1 hydrogen left, and it is now going to have the 1 original carbon that was attached to it, and now these 2 carbons are also going to be attached to it. 1, 2. So this is a secondary amine. There's 2 carbon branches attached to it. So N-methylethanamine would be the name of this guy, because the parent is the ethanamine, or aminoethane if you want to go with that. But the nitrogen also has a methyl group on it, so N-methylethanamine would be a good name for it. Then let's do the same thing. Let's take the secondary amine and run it through a secondary reaction. So this nitrogen, which has 1 remaining hydrogen, we can switch that out. So let's draw our original, and line diagrams really shouldn't have dots on them. I'm just trying to make it obvious. Let's make it look proper. All right, so there is our N-methyl aminoethane or ethanamine, whatever name you want to go with. And we can add to that, let's choose another alkyl halide, and for fun, let's go with a, who haven't we used yet? Let's use fluorine. So this guy here is a 2-fluoropropane. We can do this substitution reaction just like before. The hydrogen is leaving with the halide, so we get a hydrogen halide. And where the halide was attached, in this case carbon number 2 on the propane, that's where it's going to attach to the nitrogen. So the nitrogen originally had these 2 carbons and that carbon, our N-methylethanamine, and now it is going to have this propane attached to it. So the middle carbon of the propane, carbon number 2, that used to have the fluorine, I've just rotated it 90 degrees here, is going to be where it attaches, because that's the one that lost the fluorine here, and the nitrogen lost the hydrogen, and so we'd end up with this ethyl group and a methyl group. We want to put them alphabetically, so we'd say N-ethyl, N-methyl, and then we have our propane here, so it's a propanamine on it, and we can say 2-propanamine because the amine is on the second carbon. It could have been on the first one, but it's on the second one here. So our 2 products would be this hydrogen halide. Oh, I got 2 pluses here. Hydrogen halide and this tertiary amine that is called N-ethyl N-methyl 2-propanamine, or propan-2-amine if you want. Hydrolysis is another type of substitution reaction, and we see these with esters being broken down or amides being broken down. So remember, an ester has the sort of 2 components to it. So you can imagine what used to be like an alcohol component, and then let's draw a, let's go with maybe 3 carbons here, just so our 2 halves are different. So there's our ester, and again, the name of the ester, we start with the alcohol name. So this is ethyl. Name the alcohol component first, and you can tell which one's the alcohol component because it doesn't have the double bond on it. It doesn't have that functional group on it. It's just attached through the oxygen. So we have our ethyl branch over here, and then we have 1, 2, 3. So that's a prop, but it's an ester. So it would be prop and O8. So we have ethyl propanoate, and what we could do with that is we could split it apart. So this is a substitution reaction, but we are using water to split it apart, so a hydrolysis reaction. And I'm going to imagine water as being a hydrogen and this alcohol group, just to make it a little bit easier. And when we do this, think of it like breaking right here. And the hydrogen is going to go to the oxygen, and the alcohol group is going to go to this other carbon that is here. So we're essentially breaking this bond right here, and we're going to stick the hydrogen on one half and the alcohol group on the other. So what used to have just an oxygen that was bonded to the rest of the ester, it's going to get the hydrogen, and then the other product that's going to be produced, we can imagine this used to be the acid part of the ester, so it used to be the rest of the ester here. So this carbon here is going to pick up the OH remaining, and so we end up with an OH group on there, and so we produce this 2-carbon alcohol. The used to be an ethyl branch of the ester is now ethanol, and we've produced this 3-carbon now carboxylic acid. So this would be propanoic acid. So this is a splitting of an ester using water, hydrolysis. You can do the same thing with an amide. So let's use a similar example. So let's choose an amide. In this case, they're connected through the nitrogen. And again, we have this double bonded O, and let's use the 3 carbons so it's comparable here. We're going to use water to split it apart, hydrolysis again. And same thing's going to happen. The water, 1 hydrogen goes to one side, in this case the nitrogen, and then the OH goes to the other side. So we end up with an amine. Let's draw the amine first, reverse the order versus the name. So that nitrogen there, and it already did have a hydrogen because, you know, it's got 2 bonds, so it already had 1 hydrogen. So let's actually write the second hydrogen on there. So the hydrogen from the water is going to be added to that nitrogen. And then the other one, let's make sure I got the carbons right. So this is where the double bonded O is. So this carbon here, it's going to end up getting the other half of the water, the OH group, and you recognize that. That's the carboxylic acid. So we end up with ethanamine being produced, or aminoethane. Ethanamine, and again, because it's eth, we only have two, so we don't have to say which carbon the amine is on. It's only one option. And then we have this acid being produced, and you'll recognize it as propanoic acid. Condensation reactions is where we're essentially doing the opposite of what we just did. So you can imagine taking a carboxylic acid. So let's go with, let's try to get it to line up here. So let's go with the OH on this side, double bonded O here. And so we have a 2-carbon carboxylic acid. And let's add to that, I don't know, let's go with everyone's favorite, 2-carbon alcohol. So there's the 2 carbons, and they're on the OH. Remember that the bond that points to the oxygen, there is no carbon on the end here. So that's not a thing. This is carbon number 1. This is carbon number 2. So it kind of looks like a propane. Like if you got rid of the OH, it would look like a propane. But that bond is actually pointing to the OH. So remember, this is only a 2-carbon one, not a 3-carbon one. So we have our ethanol. And this is our, again, 1 carbon there, 1 carbon there. This bond is pointing to the oxygen, so there is only 2 carbons here. So this is our ethanoic acid, also known as vinegar. And when we add these two together, we're going to get, let's do this, this hydrogen and this hydroxide, they're going to come off as our water, hence our condensation reaction. The water comes out of it. And then I'm going to draw the carbonyl group first. So that's the 2-carbon acid component, and it is now going to be bonded to this oxygen here. So I'm just going to flip that guy around, and so we'd end up with our ester here. And in this case, we have an ethyl branch. That's the former alcohol part. That's the ethyl. And then we have 2 carbons making up the rest of it. So we leave a space, and we say ethanoic acid. So that's how you'd produce ethanoic acid, by reacting ethanoic acid. Sorry, I said that wrong. Let's fix that again. This is an ester, not an acid anymore. So ethanoate, that's what we want. And so ethyl ethanoate is produced from ethanoic acid and ethanol reacting together under the right conditions. Same thing can happen with a carboxylic acid and an amine. We can use that to produce an amide. So let's use the same. Let's say we had some leftover vinegar. And so we'll use the carboxylic acid again of ethanoic acid. But in this case, let's use a 2-carbon amine instead. So comparable to the Bell reaction. But remember, this guy has 2 hydrogens on it. So what we can do is we can take off one of those hydrogens and we can combine it with this OH group over here, and that's our water. That's our condensation out. I'll draw the acid component first. So there's our 2-carbon acid, and it is now going to be bonded to this nitrogen, which has itself 2 carbons on it. So I'll just flip them that way, and we'd end up with our the 2 carbons attached through the nitrogen. So this is our amide. So we'd say N-ethyl ethanamide. So the nitrogen has the ethyl attached, and that's this component right here. And then we have our 2 carbons over here, so that is going to be our eth, and it's an amide, so we end with amide as the name. Last group is elimination reactions. We'll look at a couple examples of elimination reactions where we're doing some shifting around with this one. These are not as clean cut as the last two. Dehydration, as the name would suggest, we're getting water out. It's not a condensation reaction because we sort of are just taking it out of one molecule. So if you have something like an alcohol, so let's say we had our, I don't know, a bunch of rubbing alcohol, and we could dehydrate this 2-propanol. Again, there's a lot going on in terms of getting the conditions right necessary to do this, but we could remove the water, and in doing so, the OH group is coming off, but it's coming off as water, so it has to be getting a hydrogen as well. So you can imagine if this carbon here, it has an OH on it, and so what we could do is we could take that OH group off, and then we need to also take off a hydrogen from this, and so we're going to end up with a alkene. So this is going to end up double bonded because the OH is gone. So this carbon here, and say either this carbon or the other one, will have lost the hydrogen, and so we end up with our alkene being produced, in this case propene. Oxidation, a little bit more common of a reaction that we could see. We're going to generically just represent whatever is causing the oxidation as an O with a bracket around it. It could be like oxygen gas, but just something that is going to cause the oxidation of a organic molecule that we're focusing on. So in this case, it's a secondary alcohol, let's say. And when we oxidize a secondary alcohol, let's look at that. So we're going to be taking a secondary alcohol. Let's use the same one we just did there. So our 2-propanol. And if we oxidize it, and we won't worry about getting even the equation balanced this time, let alone the conditions. But what's going to happen is we're going to be using it. If we're using oxygen gas, we can end up producing water from this OH group. And we're also going to be, from the oxidizing agent here, we can take the hydrogens away. So imagine, let me write this a little better. Imagine that being the OH, and then this carbon, again, remember it has an H as well. So if we take those out and we produce water, what we can end up doing is leaving behind a carbonyl group of double bonded oxygen. So in that case, we'd end up producing a ketone if we oxidized a secondary alcohol. If we had a primary alcohol, so let's take our 2-carbon alcohol. So there's our ethanol. And let's say we oxidize it. So if you leave ethanol out in the atmosphere, the oxygen is going to work through oxidation. It's going to oxidize that alcohol. And it happens in your body too. This is going to produce an aldehyde. And so the option for aldehyde is going to be that we're going to get this double bonded O on the end. You can think of it as the oxygen, in this case, if it was oxygen gas, is going to be taking a hydrogen from the middle carbon, and a hydrogen from the final carbon, and therefore, because let me draw the original, so there was a hydrogen here and there was one here that we didn't draw. If you take those guys out with the oxygen, you're going to form water, and you're going to end up forming a double bond there. That's an ugly looking aldehyde, but you'd end up with this ethanol being produced. So you're taking your ethanol, oxidizing it into ethanol, and you get water out of it as well. Then what we could do is we could take that ethanol, this is what our body does because ethanol makes you feel terrible, but what your body will do is it'll say, okay, let's further oxidize that. So this aldehyde ethanol, if we continue to react it, in this case an oxidation reaction, we can take what was a somewhat unpleasant molecule, ethanol, and we can oxidize it into a carboxylic acid. So you can imagine if we have this, let's leave that as our carbonyl group. We have this double bonded O here, and then we can further oxidize it. There's still a hydrogen on this guy. So you can imagine it's as if we sneak in another oxygen here with a hydrogen attached to it. And so you'd end up with a much more pleasant 2-carbon carboxylic acid, also known as ethanoic acid. Very easy to handle.